Hello and welcome to my admittedly low-tech video about sketching solids of revolution by hand. There's lots of cool stuff out there for sketching solids of revolution, on Mathematica, all those cool applications, but I want us to be able to do this by hand because I think it's very important for us to be able to draw sketches by hand to compute these volumes of these solids of revolution. In my 30 years of teaching calculus, I've noticed that those students who can visualize and sketch solids of revolution generally don't have any problems with finding their volumes. Conversely, those students who struggle to visualize these solids and sketch them, they generally struggle with finding the volumes as well. So I'm making this short video to demonstrate how to generate oblique views of these solids, keeping in mind that we're trying to represent a 3D object on a 2D sheet of paper. So here I have a couple of examples of 3D oblique views. They might not seem to make much sense when you look at them right here, but what I want to do is I want to put them up against the shaded picture. So for this one right here, I'm going to put it over the top of the same picture with the shading in it to kind of give us an idea of what this is supposed to represent. So you can see then that my dashed line right here is the axis of revolution. These other dashed lines inside of here are hidden lines. You can see this little curve right here. That's this curve right here. So when we look at this from that direction, that's the oblique view, is looking from that direction. We're kind of looking down in that direction. That's why you can see this face right here. This little piece right here is missing. That's what we're trying to represent with this dashed line right here. So I could literally take my pen and slide it all the way through here because it's hollow on the inside. So this is what the nice picture looks like with all the shading. This is what we're going to come up with without the shading. Likewise, for this other picture that I have here, if I were to slide this over the nice, neatly shaded picture, it might make more sense with the shading. So you can see then with the shading kind of gives you some perspective, gives you some depth here, because again, we're trying to illustrate a 3D picture on a 2D sheet of paper. So these dashed lines right here, that's this dashed line right here, that's kind of the stuff that's missing. So I could put my pen partly in there, but it's not going to go all the way through. It's going to bump into this wall that's kind of created in the back end here. So that's kind of what we're trying to represent with our 3D picture, the oblique view. So I want to practice some of these. So for starters, I want to take a look at this picture right here. Typically what you're doing in your calculus class is you're starting with a region in 2 dimensions in the XY plane, and you're revolving it about some axis. So let me start by revolving it about the x-axis. So when I revolve this about the x-axis, I'm going to create my oblique view out here on that x-axis. So I'm going to extend the x-axis. This point right here is going to correspond to a point somewhere over here. It's going to have a matching point down here, that same distance, whatever distance above, we're going to have one that's going to be the same distance below, somewhere right around here. And when I revolve that edge, it's going to look something like this. So depending on whether we're looking from that direction or from that direction, if I'm looking from that direction, then this other edge is going to be hidden. Let me show you what I mean by that in just a second. This line right here is going to still, or this curve right here, I refer to that as a line, but it's really a curve. Topologically, of course, it is a line. Got a one down here that matches it. So I didn't draw that very well, but you can see this line right here is going to be the hidden line that you're not going to see if you're looking from that direction. So if you're looking from that direction right there, you're not going to see that line. Okay, so the purpose, of course, of drawing these oblique views is to kind of help us to visualize what's happening when we're trying to find the volume. So I'm going to use a vertical slice here. That vertical slice has a thickness of delta x. That's kind of important. This point on the curve right here is going to correspond to a point somewhere over here on a curve, let's say right about there. And when I revolve that, it's going to look kind of like this. we're going to see then is that disk right there. So what we want to do then is we want to find the volume of this disk. This thickness of delta x here is going to be the same as the thickness right here, delta x. So my delta V, that is the volume of that one thin slice, is going to be the area of the face, which is pi r squared times the thickness, which is delta x. So the key in these problems is typically finding out what the radius is. This one's pretty straightforward. This radius is the distance from here to here. There's my radius. There's my little radius right there. That's going to be the same as the distance from here to here. There's my little radius over here. So you may have noticed that I've intentionally drawn it like this so that you have a one-to-one correspondence. This point right here corresponds to that point right there. This point corresponds to that point. So our radius is this vertical distance right here. Well, how do you find a vertical distance like that? You take the y value here minus the y value here. The y value here is x squared. The y value here is 0. So x squared minus 0, x squared. That's our radius. And of course, we still need to square that. The overall volume then, to find our overall volume, what we do is we're going to add up the volume of all these slices and take the limit as delta x goes to 0. We do that in the form of an integral. So all this stuff is going to get integrated. Pi x to the 4th. Delta x becomes a dx. That's kind of a big deal because I always ask my students, how thick is this? Is it delta x or is it delta y? It's kind of a big deal because if it's delta x, that delta x becomes a dx, and therefore everything inside of here has to involve x. You can't have any y's floating around in here. Also, your limits of integration are going to be x values. So I didn't note this here, but this should have been, I should have pointed this out. This is the point 1, 1. And so this is actually x equals 1. Our x values then are going to go from over here at x equals 0 all the way over to, all these slices are going to go all the way over to here at x equals 1. So that would be the volume. Well, let's take that same shape and now I want to revolve it about the line x equals negative 1. So this point right here, when I bring that down here, is going to be a point somewhere about here. That distance that I have to the right of my axis of revolution, I'm going to have a matching point over here to the left of it. So be somewhere way over here. And when I revolve that about the line x equals negative 1, we're going to get some sort of an oval here. This vertical line segment right here, it's going to look like that. Got one matching it over here. And then what we're going to do is we're going to revolve this point about the axis as well. It's going to give us another oval. This piece here is going to be hidden. So if I'm looking down from the top, I'll be able to see into the top kind of, but this line right here is going to be hidden. This curve right here, this curve is going to correspond to a curve that's going to look kind of like this. It's going to be hidden. And right where that point is right there, it's going to stop right there. So I've got this perfect correspondence here. That's that point right there. I've got one matching it over here. It's going to look kind of like this. And we should have symmetry here. That's going to map out this hole then that's missing. There's my hole that's missing. Because again, I'm revolving about x equals negative 1, so if I were to put my pen right up in there, there's going to be a gap in the middle here. So here's that missing gap right there. So what I want to do now is I am going to find the volume of this solid right here. So the way I'm going to do that, find that volume, I'm going to use the disk washer method again. So with the disk washer method, if I want to use the disk washer method, my slice always has to be perpendicular to the axis that I'm revolving about. If I'm revolving about a vertical axis, I'm using the disk washer method, I've got to use a horizontal slice. So here's my horizontal slice. That's a thickness of delta y. It's a small increment in y, as opposed to this small increment in x. This slice right here, when I revolve it about the axis, when I bring that down to my picture, see that point right there? Looks like it's a little more than a third of the way up, so I'll go a little more than a third of the way up here. There's my point. I revolve that it's going to give me something that's going to look kind of like this. I know this is hidden, so I really should be drawing this dash, but I like to look at the shape, the disc, or in this case the washer, as if I'm actually somehow able to look through there, just so I can kind of see better what's happening. So you can see we're going to get a washer here. So again, because of this angle thing right here, we're going to have stuff that's missing here. This is going to be empty in the middle here. It's going to be hollow. Okay, so now what I want to do is, this was delta y here. It's going to be delta y here as well. The delta v for this one is going to be pi r squared. It's going to be big R squared minus pi little r squared times delta y. So when I talk about big R, I'm talking about the big radius. That radius is going to go from here, from the center, all the way to the outside here. That's my big R. So big R goes from here to here. Remember, this is my axis of revolution, so that's going to be the center of that circle. So from here to here. So if I take that back up to my original picture, the distance from here, from the center to here, that's my big R. If I take that back up to here, it's going to go from here to here. How do you find a horizontal distance? You take the rightmost x value, which is 1, subtract the leftmost x value, which is negative 1. 1 minus negative 1. So big R is going to be 2. Big R is 2. The small radius then is the distance from here to here. This is my smaller radius from here to here. So there's my smaller radius from here to here. That's my little r. Little r goes from here to here. Right up to that point right there. Taking that back to my picture back over here, that corresponds to here. Remember, this was our slice right here. This was our horizontal slice. Little r goes right to there. So this is little r. So we take the rightmost x value minus the leftmost x value. The rightmost x value comes from the curve, but we have to solve this thing then for x. So it's going to be x equals the square root of y. Just rearranging this. Of course, we're in the first quadrant, so x is positive, so we're choosing the positive square root of y. We take the x value here, which is the square root of y, minus the x value here, which is negative 1. Of course, it's going to become the square root of y plus 1. Square root of y plus 1. That's our little radius. Okay, so we can turn this then into our formula for our volume for the whole thing. Again, we add up all of these volumes of all these slices, take the limit as delta y goes to 0. We do that in the form of an integral. So we have 4 minus, I'm just going to keep this as is, square root of y plus 1 squared. Delta y becomes a dy. Our limits of integration then are going to be y values. So again, the thickness here, when we say that the thickness is delta y, that's important because that tells us that the stuff inside of here has got to be y values, but also the limits of integration have to be y values as well. So the y values are going, our horizontal slices, remember this is our horizontal slice here, they're going from way down here at y equals 0 all the way to up here at y equals 1. So I want to point something out before we move on to another problem, is that when I'm revolving about an axis like this, I revolved about x equals negative 1, I always draw my oblique view on that same axis that I'm revolving about. And the reason for that is because then I've got this perfect one-to-one correspondence between the radius on here and the radius back up in here. So big R was from here to here, which matches that. Little r was from here to here, which matches that. I got a perfect one-to-one correspondence. So you'll notice that I'm always drawing my oblique view on the extension of the axis that I'm revolving about. Let's try another one. We're going to revolve now about the line y equals -2. So again, I can start off with any one of these points. I can take, let me do this. We could do what we did in the previous problem and look at it from that perspective, looking from the left-hand side, so to speak, or we could look at it coming kind of from the right-hand side. So just for fun, let's try that one. So let's look at it kind of from this direction. So I'm going to start then with this point right here. Bring this over here. Got a matching one down here. So whatever distance that is, we should have the same distance down here. If I'm looking in that direction, then I'm going to be able to see this whole end here. These are going to be visible lines right here. This line right here is going to correspond to that same line. So that same angle that I've got right there is going to be the same angle here. In fact, I'm going to bring this straight across here. It's going to be kind of somewhere right around, bringing this straight across, somewhere right around there. And I got a matching one down here. And since I'm looking at this from that perspective, I'm going to be able to see this curve right here, that line right there. I will not be able to see this one right here. Because again, I'm kind of looking at it like that. This line right here, I'm going to bring that straight across. It's going to correspond to a line right here. And I got a matching one down here. And then all of that's going to be kind of hidden also, but that's going to be what we're missing. That's our missing piece kind of in the middle. So this thing is hollow all the way through here, and it's hollow because there's a gap right here between the region and the axis of revolution. That's why this is hollow, and I could slide my pen straight underneath there and kind of move it back and forth if I wanted to. Okay, so just for fun on this one, I'm going to do this two ways. I'm going to use a vertical slice, and I'm going to use a horizontal slice. So let's try a vertical slice once. I'm going to move this just a little bit off center here just so I can kind of emphasize what that looks like in our oblique view. Well, what's the thickness, delta x or delta y? This one's going to be a delta x. So I bring that over here. Notice that height right there. I'm going to bring that straight over here and use the corresponding height, this corresponding point over here. When I revolve that, it's going to look something like this. And of course, we're going to be missing the stuff in the middle. So what we're going to get here is another one of those washers. So to find the volume of that washer, I'm going to call that delta V, just for that one washer. Again, it's going to be pi r squared minus pi r squared times the thickness. The thickness in this case being delta x. So again, this is going to be a delta x because this was a delta x. So our big radius, the big radius is going to go from here to here. Here's my big radius from here to here. When I bring that over here, that's from here to here. So my big radius again goes up to here. It's my big radius. That's what we're calling big R. Little r is going to go in there. So big R goes from here to here. On my picture over here, we have that same correspondence. So again, the reason that I always draw my oblique view on the extension of the axis that I'm revolving about, because then I have this perfect one-to-one correspondence. I can bring that radius right back over here and look at exactly what it looks like. So that radius, then, that big radius, is going to be the y value. Remember, anytime you want a vertical distance, you take the top y value minus the bottom y value. the top y value is going to come from this point right here, which is negative x plus 4, minus the bottom y value, which is negative 2. This becomes a negative x plus 6. It's going to go in here, negative x plus 6. Small radius goes from here to here, so here's our small radius. Little r goes from here to here. Again, if I bring that back over here, that's going to go from here to here, my axis of revolution, so from here to here. So again, to find a vertical distance, you take the top y value, which is 2, y equals 2, minus the bottom y value, so little r is the y value here, minus the y value here. It's going to be 4. Little radius is 4. And we could clean that up just a little bit. In fact, let me just go straight to the formula for the overall volume. Of course, we can factor out the pi. I'm going to leave that as a negative x plus 6 squared minus 16. Delta x becomes a dx, which means then that everything inside of here has got to be x's. Sometimes you get to this point, you've got some y's floating around here. You know you did something wrong because everything's got to be in terms of x. Our limits of integration are going to be x values, and the slices are going all the way across here, from here, which is x equals 0, to over here, which is x equals 2. So I'm going to take a look at that same problem one more time. Instead of taking a vertical slice, now I'm going to take a horizontal slice. So I've just reproduced that picture that I already had, just in the interest of time. So here is the oblique view that I had already had. So I'm just going to take a horizontal slice now. Well, how thick is that horizontal slice? This is now going to be a delta y. So this point right here, again, in order to be able to find our radiuses, it's much more convenient to be able to extend the axis that you're revolving about and draw your oblique view over here, because then now I can bring this point straight across here, and my point I'm talking about is going to be a point somewhere right around here. So that's going to be this point right here. This point corresponds to that point, going straight across. And when I bring that down, it's going to hit the bottom of this thing, so to speak, looking in that direction. And then I'm going to have something that's going to look kind of like this. I have another corresponding point down here. And we're going to have this thin cylindrical shell. So I know that the primary purpose of this video was to illustrate how we draw oblique views, but I think it's important also to look at what we do with that oblique view. So I do want to take a look at what this is going to look like. This is going to come straight down here. And then if you're looking at this thing, again from that angle, these are going to be dashed lines here, and you have this really thin cylindrical shell. There's our thin cylindrical shell, and we've got the real thin thickness here and here. So there's my thin cylindrical shell. And what I'm going to do now is I'm going to cut that thing with a pair of scissors, and I'm going to lay it out flat. So I'm going to slide this down a little bit. Imagine now I'm going to take a pair of scissors, and here's my pair of scissors. I'm going to cut this thing. I'm going to put my scissors inside of here. I'm going to cut this thing and lay it out flat. And what that's going to look like is something that's going to look kind of like this. It's going to have just a little bit of thickness. And it's going to look kind of like that. And it's going to extend down here, somewhere down here. But I'm kind of running out of camera space here. So But I'm going to cut it and lay it out flat. Now, I realize it's not exactly flat because the inside radius and the outside radius are a little bit different, but remember, we're going to take the limit anyhow as delta y goes to 0, so that'll all take care of itself. So, we said, first of all, that whatever axis we're revolving about, we're going to draw an oblique view around there. When I cut these things and lay them out, I'm going to go perpendicular to that again because, again, I want this perfect one-to-one correspondence. So when I lay this thing out flat here, what I need is I need the thickness, which is going to be delta y. That's going to match my original picture. That's my delta y. I need the distance from here to here. That distance from here to here is the same as the distance from here to here, which is the same as the distance from here to here, which is the same as the distance from here to here. And that matches what we have in our picture from here to here. From here to here. Okay, so that's going to be our horizontal distance there. Well, how do I find that horizontal distance? I want to take the x value here minus the x value here. So it means I need to solve this thing for x. I need to solve this equation for x because this x value comes from the curve. That would be x equals 4 minus y. So the x value here is 4 minus y. The x value here is 0. This distance then from here to here, from here to here, which again matches it from here to here and from here to here, from here to here, 4 minus y. 4 minus y. Now, obviously, I didn't draw this to scale. I should probably put some sort of a break in here because that's not really drawn to scale. But this distance right here, that height right there, so to speak, that comes from the circumference of this thing. Remember what we did is we cut this thing and laid it out flat. So really, this distance from here to here is really the circumference. That's going to be a 2 pi r. 2 pi r. And what I need to do is figure out what the radius is. So going back to my picture again, the radius is the distance from here to here. Here's my radius from here to here. So my radius is this radius right here. That radius right there, again, corresponds to the radius, the distance from here to here. Well, how do you find a vertical distance? You take the y value here minus the y value here. Well, the y value up here is going to change because that's our slices. Those are going to change. So the y value on the top is just y. The y value on the bottom is negative 2. Becomes y plus 2. So our radius is y plus 2. So that distance from there to there again matches the distance from here to here. That's going to be y plus 2. The volume then of just this one slice here is going to be this times this times this. And if I want to find the volume of all of those slices, and as we take the limit as delta y goes to 0, we do that in the form of an integral. It's going to be the integral of all that stuff. Very formal math term. Stuff. Delta y becomes dy. And again, because of the delta y, it's going to become a dy, but all the stuff's got to be y's. If you got x's floating around in here, you did something wrong. So we need to make sure these are all y's, but secondly, our limits of integration are going to be y values. So let's go back to our picture. These slices are going from down here all the way to up here. So from all the way down here at y equals 2 to all the way up here at y equals 4. From 2 to 4. There's our volume. So again, I think it's really, really important to practice drawing these oblique views because if you can draw the oblique view and visualize what's going on in your oblique view, it's very simple to find out what the radius is supposed to look like. If you're just drawing the 2D view here, not really thinking about what this thing really looks like in 3D, makes it more difficult. So I find that being able to draw the oblique views not only pays dividends here, but also a lot of you guys are going to be going into engineering. When you're looking at moments of inertia, centers of mass, those kinds of things, it's very nice to be able to visualize these things later on. So I would really encourage you guys to spend some time practicing drawing those oblique views.